Hey guys, so in this video I'm going to discuss exponential distribution and gamma distribution. So firstly I'm going to start with gamma distribution and I'm going to find the expected value, the CDF and the variance of gamma distribution, and then I'll do the same for the exponential distribution. The point of doing this is to introduce you to different distributions. Though I have to make some more videos on joint continuous distributions and discuss some more questions that I'll be doing in the coming week. Moreover, my another series on multivariable optimization is going on, so do check that out and please be with me. I'm also going to share the working of what I'm doing after I've completed the whole video. I'm going to attach the link of my PDF, so please go and see to it, and if you find anything wrong in that or any discrepancy arises, please let me know in the comments. And finally, do like the video, share the video and subscribe the channel. Thank you. Hmm. So let's start now. So I'm going to start with gamma integral. I'm going to find the expected value, the CDF, the moment generating function of gamma integral, right? Of gamma distribution. Wait a minute. Of gamma distribution, I'm going to find the expected value of gamma distribution, the variance of gamma distribution, the moment generating function. But before that, I need to explain you what is gamma integral, right? I have explained this in one of my videos previously, but I want to discuss gamma integral again so that you guys know what I'm doing, right? So this is gamma integral basically. Gamma integral is lambda e to the power minus lambda x into lambda x to the power alpha minus 1. This is a kind of gamma integral, right? So I can also write this as, if I just substitute lambda x as t, I get lambda dx is equal to dt. Lambda dx is equal to dt, right? And when x goes to 0, my t goes to 0. When x goes to infinity, my t goes to infinity. Therefore, we don't have to change the limits. M alpha lambda e to the power minus t, because we are writing lambda x as t. So this becomes lambda e to the power minus t and t to the power alpha minus 1 d. Now lambda dx is equal to dt. So dx becomes dt upon lambda, right? So this gives me dt upon lambda from 0 to infinity. Now this lambda and this lambda gets cancelled and I finally get m alpha, which is the gamma integral as 0 to infinity e to the power minus t to the power alpha minus 1 dt. And this is the kind of gamma integral that you will find in most of the textbooks of statistics, right? So I hope you guys don't get confused with this. Now let me tell you what is the value of the gamma integral. Gamma integral possesses a certain value, and I'm going to show you what the value of gamma integral is. So gamma integral is basically equal to, if I have gamma alpha plus 1, if I have gamma alpha plus 1 here, this will always be equal to alpha times gamma alpha. Gamma alpha will be equal to alpha times alpha minus 1 times gamma alpha minus 1, right? Therefore I can say that gamma alpha plus 1 equals alpha into alpha minus 1 into alpha minus 2, so on and so forth till 1 into gamma of 1. Gamma integral 1, right? I hope you guys are understanding. So if I write, wait a minute, let me just explain you how this result came about, right? So gamma alpha plus 1 is equal to alpha m alpha. Now I can write this as alpha times alpha minus 1 m alpha minus 1. Now alpha into alpha minus 1, then this can be written as alpha minus 2 m alpha minus 2, and this can so on and so forth be written as alpha minus 2 into alpha minus 3 m alpha minus 3, and so on as we go. We'll reach to this result. We'll reach to finally this result. This is our final result. Now I'm going to copy this. right? Now the value of m of 1 is equal to, now the value of m of 1 is 0 to infinity e to the power minus t alpha minus 1 dt. So this was equal to m of alpha, right? I just explained you how this came about, how this result came about. So I explained you this above, right? I'm just using this result. So now I can just substitute 1 in place of alpha. So this will give me 0 to infinity e to the power minus t to the power 1 minus 1 dt, which becomes 0 to infinity e to the power minus t dt. And we know that if I integrate this function, this will give me e to the power minus t minus 1 from 0 to infinity, which gives me minus e to the power minus infinity minus e to the power minus 0, and this becomes minus of minus 1, which is plus 1. Therefore my m of 1 gives me positive 1. I just performed simple definite integral here, right? I hope you guys can understand this, otherwise things will get very difficult moving ahead. So this is a very standard operation that I did. I just differentiated, so integrated this. So the integral of e to the power x dx, e to the power x dx is equal to e to the power x only. And if I have integral of e to the power minus x dx, this becomes e to the power minus x minus 1. And if I have e to the power 2x dx, this becomes e to the power 2x divided by 2. But now I also had limits here from 0 to infinity, so I just substituted the limits here, 0 to infinity, right? I'm just explaining you what I did, right? But now I'm going to remove this, otherwise you guys will think that why am I explaining these simple things? Everybody knows these things. I'm just explaining you this stuff, right, the integral part, so that any new viewer that is coming to my channel can easily grasp what I'm doing, though you need to have some amount of knowledge about integration and differentiation when you are trying to study statistics at a higher level, right? So now we have gotten this result. Now if I just substitute this result in this expression, I'll be getting m alpha plus 1, alpha minus 1, alpha minus 2, so on till 1 into m of 1. Now this gives me m alpha plus 1 as, now this is equal to 1. So this becomes alpha into alpha minus 1 into alpha minus 2 till 1. And what does this mean? What does this expression mean? This expression means m of alpha plus 1 is equal to alpha factorial, right? So if I have alpha equals to 2, so this becomes 2 plus 1 is equal to 2 factorial, or m of 3 is equal to 3 factorial, is equal to 2 factorial, is equal to 2 factorial. If I have m of 2 where alpha is equal to 1, this becomes 1 factorial equals to 1. And what does m of 3 mean? M of 3 simply means when I have an integral e to the power minus t to the power, now alpha minus 1 should come here, right? So alpha minus 1 becomes, alpha is equal to 3, so this becomes 3 minus 1. This should be alpha minus 1, right? So this becomes 3 minus 1 dt, which is equal to 0 to infinity e to the power minus t to the power 2 dt. Now m of 2 becomes 0 to infinity e to the power minus t to the power 2 minus 1 dt, which is equal to 0 to infinity e to the power minus t dt. See how simple the question became. Now let's start with gamma distribution now. gamma distribution. So the gamma distribution has two parameters. This is the shape parameter alpha, and this is known as the rate parameter. Right? Now alpha is always greater than 0 and lambda is also greater than 0 always. So the PDF of gamma distribution is fx is equal to lambda e to the power minus lambda x to the power alpha minus 1 divided by gamma integral when x is greater than equal to 0 and 0 when x is less than 0. This is the gamma integral. Right? So can you notice something? This is actually equal to, gamma integral was actually equal to this, right? This is the first thing that I wrote while I was beginning this video. Can you notice something? This expression which is written inside the integral, this is exactly equal to, this expression is exactly equal to this numerator, right? What does this mean? This means that if I find the integral of the PDF over the value where it is defined, it should give me the value equal to 1 because it is a PDF. If we integrate the PDF of any function from the values that it is defined for, we should be getting 1, and this is defined only for x greater than equal to 0. On all values where x is less than 0, we get the PDF as 0. So the PDF doesn't exist for any negative value of x. What does this mean? If I just try to find the PDF, this means that the PDF of gamma distribution from 0 to infinity fx, this should be equal to 0 to infinity m alpha lambda e to the power minus lambda x alpha minus 1 dx. Now we already know that gamma alpha is equal to 0 to infinity lambda e to the power minus lambda x to the power alpha minus 1 dx, or can also be written as 0 to infinity e to the power minus t to the power alpha minus 1 dt. Now if I just zoom a bit, I can write this 0 to infinity fx dx as, now if I just try to write this separately, I'll be getting, this becomes right, because m alpha is a constant term, right? M alpha is a constant term, I just showed you guys above. So lambda e to the power minus lambda x to the power alpha minus 1 dx. Now this is also equal to m alpha. So finally 0 to infinity fx dx, this gives me 1 upon m alpha into m alpha, which gives me 1. And we have proven that the value that we get after integrating the PDF over the limits for which the function is defined, the value that we get at the end is equal to 1, and it should be always be equal to 1. Now we have the value of gamma integral. Now we need to find the expected value. Let's just find the expected value. So the expected value is ex x into lambda e to the power minus lambda x to the power alpha minus 1 dx from 0 to infinity divided by m alpha, right? So this gives me e to the power x. Now I'm just writing m alpha here, right? This gives me right. So anytime we need to find the expected value, now I explained this earlier also, anytime we need to find the expected value, what do we do? We just do this x into fx dx, right? And we write the limits for which the function is defined. Actually it is minus infinity to minus infinity when the limits are minus infinity to minus infinity, but here we have the function defined for 0 to infinity, so we'll be writing 0 to infinity x into fx dx. Now m alpha was a constant term, so I just took that out from the integral. And why is it a constant term? Because I explained to you as m alpha is equal to alpha minus 1 into m alpha minus 1 and so on and so forth, and finally what we get is m alpha is equal to alpha minus 1 factorial, or m alpha plus 1 is equal to alpha factorial. Now so now if I just find the expected value, this is very simple now. So this becomes, now I have x and lambda. I can multiply this lambda x with this term inside. Now I'll be getting 0 to infinity e to the power minus lambda x and lambda x to the power alpha, because I have lambda and x here present here, right? Dx. So this becomes, now if I just try to see what does it become, if I just try to write this as lambda x is equal to t, I'll be getting lambda dx is equal to dt. So I'll be getting dx is equal to dt by lambda, dt by lambda, and this becomes e of x as 1 upon m alpha into 0 to infinity. Now lambda x is equal to t, so this becomes e to the power minus t, t to the power alpha, t to the power alpha d t by lambda. Now lambda is also a constant term, so I can take that out common. So this gives me e to the power x 1 upon lambda into 1 upon gamma integral into 0 to infinity e to the power minus t. Now I have t to the power alpha, but I need a form where I have t to the power alpha minus 1. So I can write this alpha as, alpha can be written as alpha plus 1 minus 1, right? And this will become my new thing, or the new shape parameter that will come inside my gamma integral. Let me explain you. So I can write this first. Let me complete this. So this becomes t to the power alpha, t to the power alpha. Now I can write t to the power alpha as t to the power alpha plus 1 minus 1. Now this has become like a gamma integral, the form of a gamma integral, and I can write this as e to the power x 1 upon lambda 1 upon m alpha. Now I have alpha plus 1 minus 1 here, alpha plus 1 minus 1. So what does this become? M alpha plus 1. Now let me just show you what I did. Wait a minute. See here, right? So we write m alpha whenever we have alpha minus 1 here, right? So I have alpha plus 1 minus 1 here, alpha plus 1 minus 1 here, right? I have alpha plus 1 minus 1 here, right? So I'll be writing m alpha plus 1 here, e to the power minus t alpha. Now we know that m alpha plus 1 is equal to alpha times m alpha, right? So this gives me e to the power x 1 upon lambda into 1 upon m integral alpha m alpha. Now I can just remove this and I'll be getting alpha upon lambda. So my expected value becomes alpha upon lambda. Now if I just move on and try to find, now we need to find the variance, and the formula for variance is e x square minus e of x whole square. Now we know that ex square is equal to 0 to infinity, because our limits are 0 to infinity. Otherwise, if the limits were minus infinity to infinity, I would have written the limits as minus infinity to infinity. But here I have my limits from 0 to infinity, so I'll be using that from 0 to infinity. So I'll be writing x square fx dx. So now this becomes I don't think I'll be able to cover exponential distribution also in this video. So x square, now I'm just taking out the gamma integral out from the integral, otherwise I would have written that, but it's a constant term, so I'm writing that separately in the denominator. Or let me not write this like this, I'll change it a bit. Wait, so I'll write this as, now this is a constant term, so this is outside, and this is 0 to infinity x square lambda e to the power minus lambda x to the power alpha minus 1 dx. Now I can write this as if I just zoom it a bit, I can write this as 0 to infinity. Now this becomes x square lambda. So what I can do is I'll just multiply by lambda and I'll divide by lambda, and this becomes lambda, this lambda and this lambda and this lambda becomes lambda square. So I'll be getting lambda square x square e to the power minus lambda x and lambda x to the power alpha minus 1 dx. So this lambda is a constant term, I'll just take it out from the integral, and I'll be left with 1 upon lambda. Wait a minute. Right. So this becomes now 0 to infinity. This denominator is out here. Now this becomes e to the power minus lambda x. Now lambda x becomes lambda x. Now this was alpha minus 1, and alpha minus 1 plus 2 becomes alpha plus 1. Right. So this lambda square x square is actually equal to lambda x whole square, right? And if I just multiplied this term with this alpha minus 1, I'll be getting alpha minus 1 plus 2, which is alpha plus 1. Now finally what I get is, I hope this is much better. Now this is somewhat like, if I just substitute again, lambda x as t, x goes to 0, t goes to 0, x goes to infinity, t goes to infinity, and this becomes this, for just for explanation, this becomes 0 to infinity. Now lambda x is t, right? So lambda dx becomes dt. So again, if I just try to find this, this becomes minus t, and this becomes t to the power alpha. Now this is alpha plus 1. Alpha plus 1 can be written as alpha plus 2 minus 1, and now dt is lambda, dt is dx is equal to, this was dx, so dx is equal to dt by lambda, so this becomes lambda. Now lambda comes out common, so this becomes lambda square 1 upon gamma integral, and this is actually equal to 0 to infinity e to the power minus t to the power alpha plus 2 minus 1 dt, and this finally becomes ex square, finally becomes into, now this becomes m alpha plus 2, because I have alpha plus 2 t to the power alpha plus 2 minus 1, right? Now this finally becomes 1 upon lambda square into 1 upon this, and now m alpha plus 2 is alpha plus 1, m alpha plus 1, and m alpha plus 1 is equal to alpha m alpha. So finally this becomes alpha plus 1 alpha m alpha, right? So this gives me alpha plus 1 alpha m alpha. Now this and this gets cancelled, so finally I'm left with alpha plus 1 alpha. Right? Now I'll use these two red boxes, this red box and this red box. Now my variance finally becomes my variance is equal to ex square minus e of x whole square, and this becomes now my e of x square was alpha plus 1 into alpha divided by lambda square, and this was alpha upon lambda but e of x whole square for variance. So this becomes alpha square plus alpha minus alpha square divided by lambda square. This and this gets cancelled, so I am left with alpha upon lambda square. So my variance becomes alpha upon lambda square, right? Let me see my answer. So my variance becomes alpha upon lambda and alpha upon lambda square. Alpha upon lambda square, alpha upon lambda. Now we have to discuss moment generating function. It's actually 3 AM right now, so it becomes too heavy to sometimes do these calculations at this time. Though these are very basic calculations, but still, sometimes it becomes heavy. Now we need to find the MGF, the moment generating function. The moment generating function given to us is, or moment generating function is always equal to e to the power expected value of e to the power tx, which is 0 to infinity, because our values because our limits are 0 to infinity here, e tx into fx dx, and this is known as our moment generating function m of t, right? So this can also be written as expected value of e of tx and 0 to infinity we change the color of the ink. This becomes this is vibrant, right? So this becomes, don't worry, I'll be sharing this PDF with you, so you'll be able to understand what I'm doing, right? 0 to infinity e to the power tx, and fx was, so this was a constant term, this comes out, and e to the power tx, this becomes lambda e to the power minus lambda x to the power alpha minus 1 dx, alpha minus 1, this is alpha minus 1, right? And this finally becomes now e to the power tx, so this becomes lambda e to the power minus lambda minus t into x and lambda x alpha minus 1 dx. So what does this say? This integral basically gives me lambda e to the power minus lambda minus t x lambda x alpha minus 1. So if I just substitute lambda x as t, or I need to substitute lambda minus t as t, right? Wait a minute. Lambda minus t is equal to u. Lambda minus t x is equal to u. Now my variable has changed, right? My variable has changed because earlier we didn't have t in our original integral, right? So that is why we were assuming that lambda x is equal to t is any variable, but right now I have t already present in my integral, so I'll be taking for substitution I'll be taking some other variable u, right? So lambda minus t x is equal to u. So lambda minus t dx is equal to du. So this gives me 1 upon m alpha 0 to infinity lambda e to the power minus u. Now lambda x, I have lambda x alpha minus 1 dx. So basically I can write this as u plus dx but I can write this as u plus dx. Now du, this becomes lambda minus t dx. So finally this becomes u plus tx. Yeah. So here I am just I had to make a change here. Here instead of u plus tx, I should have substituted. I should have substituted. See, because we have assumed that lambda minus tx is equal to du. We have assumed here, right? Lambda minus tx is equal to u. So lambda minus t is equal to lambda minus t x is equal to u. This basically gives us that x is equal to u by lambda minus t. This means that lambda x becomes lambda u lambda minus t, and lambda x to the power alpha minus 1 becomes lambda u lambda minus t to the power alpha minus 1. So what does this finally give us? This gives us now, in place of lambda x alpha minus 1, we have lambda u by lambda minus t alpha minus 1, right? So I can write this as 1 upon m alpha into 0 to infinity. Now if I just take out lambda and lambda minus t, so this becomes lambda into lambda alpha minus 1, and I already had one lambda minus t here, so this was lambda upon lambda minus t into lambda to the power alpha minus 1 upon lambda minus t to the power alpha minus 1 into e to the power minus u to the power alpha minus 1 du. Now this is a constant term, and this will be equal to lambda upon lambda minus t to the power alpha into 1 upon this, and this becomes 0 to infinity e to the power minus u to the power alpha minus 1 du. Now we know that this is a form of m alpha, just the variables are different. Earlier we had e to the power minus t to the power alpha minus 1 du. Now we have u. I have explained you the difference earlier, why I was using t earlier and why am I using u here, right? So this gives me lambda upon lambda minus t to the power alpha 1 upon m alpha, and this gives me m alpha. So this becomes, I can cancel this out, and finally what I am left with lambda upon lambda minus t alpha, right? So this is my moment generating function. Now we know that the first order derivative of the first derivative of m dash t, and if I put t tending to 0 here, I'll be getting the expected value. If I find the second derivative and take t to be tending to 0, I'll be getting e x square. Again, this concept I've explained in the previous videos, my initial videos, actually not my previous videos, my initial videos of fundamentals for mathematical statistics. I am also covering another series which is on mathematical optimization. That is different. That is an ongoing series, and I have made about 10 videos on that. Do check that out if you get time. So now let's just check if what we performed earlier, ex and ex square, comes out to be same as what we did earlier, right? So our ex square was this 1 upon lambda square alpha plus 1 into alpha, and our ex was alpha upon lambda. So let's just check if what we have performed so far is right or wrong. So we need to find, for ex we need to find m dash t. So m dash t comes out to be um, wait a minute, I need to find this derivative. So minus alpha lambda to the power alpha lambda to the power minus t alpha minus 1 and minus 1. So m dash t where t is now tending to 0. This is alpha, positive alpha, not t, positive alpha. So this becomes alpha into lambda to the power alpha, and now t is going to 0, so I'm just substituting 0. So this becomes alpha minus 1, and I get finally alpha upon lambda. Alpha minus 1. Wait a minute. This was alpha, right? Hmm. 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 Yeah. So lambda alpha minus 1, alpha minus 1. This becomes minus alpha. I've done something wrong. Wait a minute. This becomes alpha minus 2, right? Sorry. This becomes, after differentiating, this becomes alpha minus 2. Wait a minute. Alpha. This was alpha, right? This was alpha, right? So if I just differentiate this becomes lambda. Sorry. Lambda to the power alpha, and this is lambda minus t to the power minus alpha. Now we differentiate, this becomes lambda to the power alpha is a constant, and this gives me lambda minus t. Now minus alpha minus 1, and I have minus alpha, because this is exactly equal to minus half, 2 to the power 2x to the power minus half. If I am differentiating x to the power minus half, I'll be getting minus half and x to the power minus half minus 1. So this is basically minus half x to the power minus 3 by 2, and if I just move my x in the denominator, this gives me 3 by 2, right? So now coming back to my expression, this is alpha plus 1. This is alpha plus 1, right? So this is plus 1, and finally what I'm left with, in the denominator I'm left with lambda. Alpha minus 1. Yes, so my m dash t t equals to t tending to 0 is equal to alpha upon lambda, which is equal to my expected value. Right? Sorry for the small error that I made. I explained myself here. You can just check that out. So this is basically d by dx. I was just trying to prove you guys what I did was right. So now I need to find the second derivative. This is basically d by dt of dm by dt. So basically I need to find the second derivative, or I can also find the first derivative of m dash t. Both are the same thing. So I just need to differentiate this again with respect to t. So this becomes d by dt alpha, and this is lambda upon alpha. So I can write this as lambda alpha lambda minus t alpha plus 1. We need to find this with respect to t. Now this becomes minus alpha plus 1 and minus alpha plus 1 and minus alpha plus 1 minus 1, so this becomes minus alpha minus 1 alpha plus 2, right? And another minus 1 for t. So this finally becomes m double dash t becomes alpha lambda alpha finally becomes alpha alpha plus 1 lambda alpha lambda minus t alpha plus 2. Now we know that m double dash t when t goes to 0 comes out to be alpha plus 1 alpha divided by this will become lambda to the power alpha and lambda to the power alpha plus 2. So this becomes alpha plus 1 into alpha lambda to the power 2, right? So finally my m double dash t, where my t tends to 0, comes out to be e of x square, which is equal to alpha plus 1 into alpha divided by lambda square, right? So I've proven you guys. I don't think I should be covering exponential distribution in this video only, because we have covered a lot of things in this video. I've showed you guys how we have found out ex square, how we have found out ex from moment generating function, and if we try to find out the variance also, you can just substitute the values and you will be again getting the exact value of variance, which turns out to be alpha plus 1 alpha square plus alpha upon lambda square upon lambda square. So this becomes alpha upon lambda square, right? Now I'll be sharing the PDF. This was a bit long and sorry for the mistake that I made in my differentiation. Sometimes it happens. I've been solving this for quite some time now, and it's actually 3:20 AM, so I'm bound to make some mistakes. Please excuse me for that, right? So thank you. If you like the video, please share the video and do subscribe the channel. It is very motivating for me. When I see a comment, it makes me push myself more, right? So thank you, and I hope to see you in the next video. And please check my series where I've discussed multivariable optimization, mathematics for economic analysis, by Nuts Trader and Peter J. Hammond. This is the book that I'm referring to while making these videos. So thank you. Bye bye.